My big problem with all of these line integrals that you did in section 2 is they suck. Writing out the parametric equation for your curve, figuring out how to parameterize so that you can do the integral is just downright unpleasant. And I'm sure that when we deal with, a curve in 3D as opposed to a curve in 2D, it's even more ugly because the integral just gets bigger and messier and nastier. And I don't like doing all of the parametric work if I can avoid it. When can I avoid it? Well, if we think about breaking our parametric equation, break stuff up into little pieces and does it along the curve, that's like the Riemann sum doing it along the x-axis. That's the long pain in the ass way. And we have the fundamental theorem, which this is part 2 of the fundamental theorem of calculus. What does this mean? Well, this means that when I want to evaluate an integral, I can just look at an antiderivative. And I can evaluate the antiderivative at the end point and start point, A and B, of my interval, right? So to figure out the integral, I just need to do an antiderivative. And I need to plug in the place I start and the place I end and subtract. I want to do this idea for a line integral. But in order to do that, I need to think about what I'm integrating. When I do a line integral, I'm doing an integral of a vector field. So I do some sort of integral like this. The line integral of some vector field along some curve. That's our C is our path. What's an antiderivative for F? Oh, wait a second. In the homework, you were asked to tell me whether or not there was a function that when you took all the right derivatives, you got a vector field. Our antiderivative idea here will be some function whose derivatives give us the vector field. But if the derivatives give us a vector field, then anything can be more than one derivative. In the homework, what did we actually do in the homework that said, oh, here's a function, and when I take all the right derivatives, I get my vector field? We didn't just take one derivative, we took all the derivatives. If I think of my gradient as this derivative idea, actually, I was writing that for my gradient, right? The gradient vector field. Then I can think of this function as my antiderivative. So if we have a function f whose gradient is my vector field, then I have an antiderivative. And that means I can take my fundamental theorem of calculus and do it on a curve, on a line. So let's suppose we have a nice smooth curve and f is differentiable so that the gradient vector field is continuous on my curve. So in other words, this is the right function to give me the gradient vector field. Then to do the line integral, I don't have to parameterize squat. I don't have to write any parametric equations. I just need to do plug in the end, plug in the start, and subtract. What? Wait a minute. I need an example or this doesn't make a damn bit of sense. So here's the problem I want to do. I want to do the integral over this curve of this vector field's force. I want to know how much work is done. My integral f dot dr, right? Now, I'm the first person to tell you that if we were going to do this the way you did it in the homework, we would have to take x of t is the square root of t. Y of t is 1 plus t cubed. So dx is 1/2 t to the minus 1/2, and dy is 3t squared, right? And then I would have to do the integral from 0 to 1 of x cubed y to the 4th comma, x to the fourth, y cubed, dot, dx, dy, dt. Does that integral look like fun? No. No, this integral looks disgusting. I'm going to have to multiply out all of these polynomials. I'm going to have to distribute all of this, do the dot product. This is going to take me forever, right? F this. Please note. I have a function that I have literally just pulled out of thin air. What is the gradient of this function? Unfortunately, no, because when I do my derivative in respect to x, the x cubed stays, the y to the fourth is multiplied by it. What's my y derivative then? Hey, wait a second. That's our vector field F. We gave this a name last week. What kind of a function is F with regards to this vector field? Or what kind of a vector field is this? That wasn't the word we used. It's a good descriptor, but unfortunately it isn't the word we used. That actually has a different meaning in vector fields. The vector field is conservative, and this F is our potential function. Now, ready for the fun part? The theorem I wrote about line integrals says that if you're doing the line integral on a conservative vector field, you can just plug in to the potential function. Instead of doing all this bullshit, if I want to do the integral C f dot dr and the gradient of f is our vector field, then this equals f of r of b minus f of r of a. All I need to do, like in the fundamental theorem of calculus, is take my antiderivative, my potential function, and plug in where I start, and subtract. Wait a minute. That means I need r of t. R of t. I go back up here. There's R of t. What do you get when you plug in 1? I need, that's A, that's B. So I need B. R, not F, R of 1 is what's R of 0? So I take F of 1, 2 minus F of 0, 1. But wait a minute, F is this function. When you plug in, what do you get? Unfortunately, no, it isn't, because that's a 0. So it's 16 over 4, which is just 4. Now, I want you to understand why I am absolutely happy, thrilled beyond all rational belief at this point. Because what did I not have to do? I didn't have to do this integral. I only had to get the potential function and plug in. Holy crap! The key statement is that top of the screen. If I have a conservative vector field and I know the potential function for it, I know the antiderivative, I can use fundamental theorem of calculus. And the fundamental theorem of calculus says take the antiderivative, plug in the ends, and subtract. That's it. So let me ask you a question. What if my path was different? The path that we have, R of t equals root ti plus 1 plus t cubed j, 0 less than or equal to t less than or equal to 1, right? That goes from the point 0, 1 to the point 1, 2, but it does it in a weird looking curve, right? It kind of, well, let's actually draw the picture. Grab your graphing calculator, set it into parametric mode. Let's draw this picture. I have technology, I should use it. There's what the picture looks like. Yes? What if I give you a different curve? Ready? Here's a new curve. I want to do the same integral, but I want to do the integral now on a new curve. And that curve is going to look like this. I'm going to call this curve 2. And I'm going to call the one we started with curve 1. We just did the integral. The integral over C1 of f dot dr was equal to 4. We worked that out. I would like to know, what is the integral on C2 of f dot dr? Now here's the problem. I don't have the parametric equations for C2. But why not? Why don't I need the parametric equations? And I have an antiderivative. I have a potential function. I know that the way to do this integral is to do this. And we start and end at the same damn place. This integral is also 4. As a matter of fact, the integral of f dot dr on any path from 0, 1 to 1, 2 must also be 4. Because this vector field is conservative. As a matter of fact, we can actually use this idea of the way our integrals are working to tell us whether or not a vector field is conservative. Our integral over C f dot dr is independent of path if only the endpoints matter. Or another way to say it is if the integral over C1 f dot dr equals the integral over C2 f dot dr for any 2 paths with the same initial and terminal points. If it doesn't matter how I get there, just where I start and where I end, that's path independent. Huh. The integral we did integrated along a path from 0, 1 to 1, 2. What if I have a closed path? What's it mean to be closed? If I end at the same point that I start, what happens when I do my line integral? No, I'm integrating along this whole path, right? But I'm integrating along the whole path. And that's the same by the fundamental theorem of line integrals. That's the same as taking the starting point value and subtracting from the ending point value. What do I get for that value? Every single blessed time I get 0. Now, this just became a brand new definition for independence of path. Go back and look at the picture we drew up at the top of this page. Scoot, 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 scoot. Here's path C1 going this way from 0, 1 to 1, 2. And there's path C2. If I did C1 backwards, so I start by going all the way around C2, and then I do C1 backwards. That's a closed path, isn't it? That gives me the value 0. And that means that the integral along the first path plus this one going the other way. Wait a minute, if I'm going the other way on a path, that just puts a minus sign in front of my integral. And if that's a closed path, this is 0, isn't it? And that means that these must be equal. So another way to determine, hey, this integral is path independent, this vector field is conservative, is if every closed path integral has a value of 0. My integrals are path independent, independent of path, if and only if the integral of C f dot dr equals 0 for every closed path C. By the way, in order to remind myself that I'm doing an integral on a closed path, we will often write the symbol for the integral with a little closed circle on it. That little circle means C is a closed path. It turns out this is not just sufficient, this is necessary, this is enough. This is all I need to know. And if my integral is independent of path, then my vector field is conservative. And that turns out to be not just necessary, but sufficient. So here's the $64,000 question. How do I know if F is conservative? Now, you were actually given functions and asked to take their gradient and say, hey, here's my gradient vector field. But I gave you this example. And I gave you this function. And I said, look, this is the right function. This is conservative. How the bloody am I supposed to know that's the right function? Where did I get it from? I said earlier, I pulled it out of thin air. That's a horrible trick. I don't want you guys to have to pull it out of thin air. That's inappropriate. How do I figure out whether or not this is conservative? This is the x derivative of this function. This is the y derivative of this function, right? That's what it means to make this the gradient of f. That's partial of f with respect to x and partial of f with respect to y. Now, normally we call these things p and q, right? When we're dealing with a vector field, the component functions are p of xy and q of xy. So what I'm saying is that fx must be p and fy must be q. Ooh, I'm taking derivatives, right? I'm going to jump back to our chapter under chapter 14. Instead of looking at first derivatives, I'm going to ask you a really stupid question. What's special about second derivatives for nice functions? When we looked at our second derivatives, how many second derivatives were there? Function of two variables. How many second derivatives did we come up with? 4 of them, right? And they were fxx, fxy, fyx, and fyy. But there was a really nice theorem that stared at me that told me something about some of these derivatives. What did I know about those derivatives? Hey, wait a second. I get this by taking the y derivative here. I get this by taking the x derivative here. This piece right here, this is py. And this piece right here, that's QX. Whoa. When I have a potential function, those two things have to be equal. Now, right now, I'm not happy with the way that sentence reads, because it says, if my vector field is conservative, then this is true. I really want to go the other way. I need to tweak this just a little bit to be able to go the other way. I really need a little bit more knowledge about the region where my vector field lives. Here's a topology set word for you, history people, that we talked about yesterday. What's it mean to be open? It's open if it contains none of its boundaries. It's got little balls around it for every point. So I want you to imagine we have our set, our region, and we pick a point. Pick a dot somewhere inside this region. I don't care where it is. There's some little circle of radius epsilon that is completely inside our region. That's what it means to be open. You can put little balls around any given point. Notice if you were on the boundary, half of your ball would be on the outside, wouldn't it? No matter how small you made the ball, part of it would still be outside. So the way you say I'm on the inside is there's a little bitty ring around me that never goes outside the region. Now, my curve needs to be in here. So again, a curve C is closed if R of B equals R of A. I'm going to add a new twist to this. A closed curve is simple if it doesn't cross itself anywhere except the start end point. So a figure 8 is not simple. A figure that crosses itself anywhere fails to be simple. A simple curve can be rather wiggly and complicated looking. But as long as it only crosses at its starting and ending point, that's simple. So I have an open region. I need one more statement about my region. A region is simply connected if it has no punctures, holes, tears, or slits. So I think of a simple curve and a simply connected region. On page 1090, there are our curves here in the upper figure 6, and here are our regions. These regions are simply connected. These are not. That's got holes, that's got holes, that's got a slit in it. I'm not allowed to use those. I want regions like this and curves like this. And when I have both of those things, then my Clause's theorem result is enough. So let's suppose I have a vector field F whose functions are P and Q. And those functions are on this open, simply connected region D. And those functions are also C1. The hell is C1 again? C stands for continuity. And that 1 means they have continuous first derivatives. In other words, I can tell if my vector field is conservative by looking at the partial derivatives as long as we're on a nice, open, simply connected region. Okay, I'm going to use this. Let me go back and look at my vector field. In the example we were just doing, we had F was x cubed y to the 4th, comma, x to the 4th y cubed. This is P, this is Q. What's PY? And QX? Those are the same. My vector field is conservative. If my vector field is conservative, I have to have a potential function. Now, we already know what the potential function is. But earlier I told you I pulled it out of thin air. How do I actually figure out what the potential function is? Well, now I know that this P must be the partial of f with respect to x. And that this Q must be the partial of f with respect to y. Hey, wait a minute. That means that I could find f by doing the integral of P with respect to x. The antiderivative. Not just a definite integral, but an indefinite integral. I could also say that f should be the integral of Q dy. You've got P, you've got Q. Let's do these integrals. The integral of P is the integral of x cubed y to the fourth dx. And over here, it would be the integral of x to the fourth y cubed dy. What do you get when you do this integral with respect to x? But wait, there's more. Say that again. I have a little bit of a problem here. This plus c is only a constant in terms of x, right? So that could be y's in there, couldn't there? I don't know. This might be some function of y. I'm even going to call it C1, because over on the other side, I'm going to do the integral with respect to y. What do you get here when you do this integral with respect to y? Which is the same thing I see over there, but now there's a constant that could contain x's in it, right? So now I have to make sure that if there's anything over here that just has x's, it has a space to go. And if there's anything over here that just has y's, it has a space to go. I have to reconcile these two things. When your vector field is not conservative, you can't make these match up. As a matter of fact, back in the last chapter, we did this integral. Example 4. We did the integral of y squared dx x dy. I can think of that as the integral of the vector field y squared x. Well, there's P and there's Q. What's Py? And Qx is 1. And those are different, right? If you tried to do the integrals here, you'd integrate this one with respect to x, you'd get xy squared. You'd integrate this one with respect to y, you'd get xy. Do those match? Can you fill the wrong pieces into the constants on the other side? No. So this is not a conservative vector field. And notice, when we did the integral two different ways, we got two different answers. This was not independent of path. The reason it wasn't independent of path was because this isn't conservative. The fundamental theorem for line integrals makes my life a crap ton easier. Now, the big problem I have right at the moment is that these are only vector fields in 2 dimensions. Do vector fields in 3 dimensions, I've got to do more work. I've got to reconcile and really deal with P and Q and R. I'm going to have to do an integral with respect to X, an integral with respect to Y, integral with respect to Z. There is an example of this on page 1092. Example 5 walks through this quite well. For the record, conservative vector fields give rise to quantities that are conserved. So when you talk about kinetic energy and potential energy is the potential function for kinetic energy. The reason we have conservation ideas in physics is because the vector fields we work with are conservative. And the places where those vector fields break down and fail to be conservative are places where we have energy loss in the system. Places where things don't get conserved, like across the singularity of a black hole. Modern physics depends on doing these kinds of things. I'm going to give you one of my favorite theorems in the entire universe that deals with this tomorrow. And we'll see you all then. Have a wonderful rest of your day.